And then we look at one sample continuous. Now, non-parametrics, probably the methods course you took was parametrics, okay? Your normal theory classes, okay, you assume the normal distribution and you do everything. In this class, we just throw away normal distribution. I don't know if you got sick of that assumption or not. I certainly did in grad school. I finally walked into a class in non-parametrics. Normal model was gone. So there's a lot we can do without normality, but we will always review the normal theory method. Okay, when we do a confidence interval, we'll put a Wilcox procedure before that or during that, we'll be doing the T interval too. So that should ring a bell, right? And we'll compare them. We can compare them on examples. We can easily generate data sets in this class, and we can, do. You can dictate the example if you want to, the parameters. So the one sample continuous model will probably be new stuff. It's the Wilcox and sign rank Wilcox and things like that. And I'll stress descriptive statistics throughout. So. And then we have the two sample problem, and that's Mann-Whitney, Wilcox, and there's a two sample scale problem also, and Behrens-Fisher problem, etc. Okay, and then the notes end. There's still a lot to do. So then what happens? Actually, I'm writing another book. It's on R, and I think we can actually take notes out of it because we have to do what's left. Well, regression. I want to do regression models, simple regression, and multiple regression, and I want to do one-way ANOVA and two-way ANOVA. Okay, problems like that, and probably I'd like to finish with ANCOVA, analysis of code. So when we get to that point in class, and, I'll put the other notes up as soon as we look at those. Okay, and there's references to them. So at the moment, that's the text. Okay, it's not really. I'll put a lot of pictures in. Any questions on that? So keep that book up, right? Okay. I put exercises up too, and then I'll pick out these. I like to assign exercises for class discussion. Okay, I'll do that every time, although I don't have any for this time. But I'll get that on the, you can always look at where we are before you come to class, so there'll be exercises there that we, I'd like to begin the lecture with discussion of exercises. Okay. I think I'm going to get a grader, so we will have some homework projects too, maybe some computer projects. So, you could just, there's a bunch of exercises. I should add to that as we go along. questions and answers. Someone for the last midterm in this class, they asked for a summary of material, so I just told her, well, send me a bunch of questions, and then I'll put the answers together, and then I'll put it on the web, so you can look at those when we get close to the midterm. Maybe you'll have further questions. Okay. Now, computation in this class. In class, I just want to use R because I can do all kinds of plots and examples with a simple command. Okay? So maybe we should talk a little bit about that. Now, R is free. It's a very powerful language in statistics. It's actually become the language of statistics, computational language. It's free and it runs on any platform. So if you have Windows or Mac or Linux, I have Ubuntu running on this. You can download it all. Okay. And there are many packages written in R. I've written one myself to John Crotty on some of this robust stuff. So if you go to a list of packages in R, you'll see there's probably about 3,000 to 4,000 packages. So many professional statisticians, like myself, we're writing things in R. So that's nice, and we can, as you'll see, we can use it in class very efficiently. So we have no problem with that. Now, what's the bad story about R? The learning curve on R is a bit steep. I realize that, and in this class, many of you are not statisticians, and you'll probably prefer to use another package. So what other packages are there? Well, I do have some drop and click stuff on the web. And we could go out and, that's probably down here on the sheet. We'll get to that. I can show that later. So I do have that, and another thing we could use Minitab. Minitab, you can learn Minitab in about 2 minutes if you don't know it. It's just a click language like it. You know SPSS, it's the same. Okay, Minitab's very simple. So these things are on Minitab. I guess I use Minitab because I got my PhD at Penn State, and at the time I got my PhD, that was like 1,000 years ago. They were just putting Minitab together, so I was there at the beginning. In fact, I wrote an algorithm for Minitab. One of the functions. I don't know if they still use mine. That was many years ago. So Minitab's easy to use, and I do have it running. Minitab's and R's everywhere, I think. It should be in every lab. Can't believe that. R. But it's also free. You can download it. So Minitab's not free, but you can get a student copy. I think lasts about a month or so. Free. You can download that Minitab. But it's also on most of the labs. They have a university license. Okay. And I do have it on an old PC. I have a laptop which is 12 years old. And I have to put in the new license every year. You have to put the stupid license number in. But once I do that, I can bring that into class and can run into it. The drop and click is called bungee. It's a browser. questions on computing? So the bottom line is you don't have to get argued on it.
What about SAS?
SAS is, I don't make much use of SAS in class. It does have non-parametric stuff too. The problem with SAS is it has a learning curve also. But you can use SAS, you can use what you want. Okay? I mean, one thing you should get in the habit of doing anyways is you have a simple example, and so you have a very simple example. Maybe you could even do the Wilcox and stuff by hand on it, so you know the answer. So when you run a package, you can always do that simple example and see if you get the same answer. You know, if you don't, then maybe the package is doing something different. Okay. That could happen on the Wilcox because there's several versions of this, like the test statistic, and they may be using a version of, it's equivalent if you do a p-value, but you won't get the same answer on the test statistic. So if you want to use SAS, you can. Okay. Or I don't know too much about SPSS. I've run SPSS. I used to direct the lab here in the staff. By the time she uses SPSS. And I'm sure it has non-parametric stuff too. Okay, any other questions on computations? Now, if you've thrown away your methods book or sold it, okay, you can get a free one. Although I don't think it has actually a non-parametric chapter. I think I have to see if I can find it. But there's a book by Rasmussen I used to use in the methods class. And, it's a very good book. The problems are really good. She has really good exercises with low data. Okay, a lot of clinical stuff. Okay, and you know, it's not the whole clinical study, of course, but she subset the clinical studies. So you know, it's real data, real situations. And, I like that book for methods. Well, and it sort of went out of print. And for some reason, she had it up on her web, which was a mistake because it was copied in India by someone, and they were selling it. So when she learned that, she just put it up on the web for free, and she let us use it. So if you want to, you can click on this methods book and you can download it if you want. But here's the chapters. I think maybe 2 is in there. It's chapter 2. Central limit. But you can use that if you want to. You can download it if you wanted to. You know, if you don't remember something like on, oh, this is central limit there, let's see what chapter 6 is. Probability. So this is really germane to today, for today's lecture. So you can make use of that if you want to. I forget where non-pair was, but I didn't think it was here. Well, she mixed the non-parametrics in with the parametrics, which I like. Any questions on that? Anyways, I put it out there so you can use it if you want to. Looks like I've lost my webpage. I put out some tables of critical values. I wrote another book in actually math stat, and I had to do tables. So it was easy to write our program to do the table in a few seconds. And I just turned those on and put them on the web here if you want to make use of it. Oh, you need a normal table? You just click on this. Of course, it's a PDF. You have to wait till it opens. Poisson, chi-squared, there's the one. I thought the day of the tables was over. I wrote this book with Hogue on math stat, and I told Bob, I said, I don't want to put the tables out there. Everyone has a computer now using this book. You can get that. P-value is much easier. Well, I said you have to have tables, and I talked to other people, oh, you should put the tables up. So I ended up putting the tables up in the book. Oh, this is a drop and click RGLM. See, it's just drop and click, like we're doing what? On sample stuff. But it is continuous stuff. And then we just, there should be an example here. Yeah, here's a big data set. And then you can just put it in. You can do plots if you want to, and like a dot plot. So here's a data set, okay. We'll do a dot plot of it, and we'll do the we'll do the Wilcoxon. But we'll also do the T, so this is probably worth looking at. Yeah, here it is. This runs an old Fortran program only. But anyways, what it does is it prints out the, this would be the non-parametric stuff. And this would be the parametric stuff. I call these side-by-side analyses. So this would be a non-parametric estimate. And this would be the estimate you did here. This is, i.e. the sample mean. Right? So that data set we had, and you see a dot plot at the moment, the mean is 31.4, and the non-parametric estimate of center is 28. So now we can look at the dot plot. So it's what, 31 and 28. Oh yeah, we have an outlier in it, and it pulled out the mean. So here's 31. So there's the mean, and then here's 28. That would be the non-parametric. So we do have that to use also. That's RGL. But it's not complete. Okay, part of it's gone away and never come back. I wrote this stuff and I just didn't feel like I had any support. And so that's when I really started writing for R. So, but it's still, we can still do a few things with it, okay? It's quick, all right? It's just drop and click. It's even easier than SPSS. Okay. Just put the data in there. Okay, any questions on the web page then? I think that's it. there'll be a midterm and a final, and then we'll have some projects. And I do have a. Oh, here's the topics. Maybe we should look at that a little bit. Okay, it's going to be a review. All right, that's 1, 2, and 3 really. We'll do diagnostics as we go, and then we get into 1 sample problems, 2 sample problems, K sample problems. That's the ANOVA. Okay, this is where the book runs out on 6. And then a correlation, independence test, and then regression. And we should end with ANCOVA. I don't see it written. Okay, and the grade's based on midterm, final, and homework. I'll figure out the weights. I have to take this quiz out. I don't think I'll have a quiz. We'll see. Maybe we should have quizzes. What would you prefer? Actually, it's like the midterm of the quizzes. If you think about it, maybe I could ask you. You could have a quiz every other week. Then usually I don't have a midterm. I like that better. Quizzes. Why don't you think about it? We'll take a look next time. I could go either way. Starting for quizzes or tests in this class, you can bring in a cheat sheet, all right? You can have at least a 1-page cheat sheet, 8.5 by 11, front and back. I don't care what you write on the cheat sheet. I will not look at it. So, put love letters on it, whatever. I don't read it, so. I don't remember things in this class. And computations for a quiz or a test will be straightforward. The line will be printout. That's why it really doesn't matter what package we use. That printout we have is a table of the estimate and the standard error. No matter what package you run, you'll get a printout like that. And that's what's important. Okay? I mean, we'll do things in class and we'll be looking at a printout. So it'll be discussed in class. And that's the important thing for the exam. I'm not going to give you a very complicated problem and ask you to do it by hand. Okay. We have a computer now, which has really made quite a difference, especially from my point of view, okay? Because I started with a slide rule. And the math major, I took a lot of engineering classes, so I didn't even think about a computer until I was a senior. We had on our course of Fortran. And I forget what the machine was on campus. It's like she had to take the cards, the runs, the instructor. So, you know, I work in non-parametrics and robust area, and stuff I work on without the computer is pretty useless to work on. It might be that part of mathematics. I don't think it requires statistics. So things have really changed a lot. Computers are so much faster now, and we store so much stuff on a computer. It's just when I ran the lab, well, this is in the 90s, I forget what year, but we finally got a disk. And it held, I think it held 79 gigabytes. And we were so excited. And now you get that on a thumb drive, right? You get even more, you get like 16 gigabyte thumb drives. And it's just fantastic what's happening. And it's been great for statistics because the job market for the stat is just fantastic. We're collecting data like exponentially, and the rate of that statistician is linear. So there's always a definite need for statisticians. So it's good to work in an area where you can tell the students that, you know, long as you're willing to maybe relocate, you'll probably get a very good job. And in a couple of years, you'll probably be making more money than I am. So I don't tell my wife that. It's a bad joke at home. I used to tell her about a master's degree graduate. Well, you should be making more than me. Wow. Okay, any questions on that? Okay, so we have what, till a quarter to. I should take a roll, make sure, hopefully first names would be okay. I'll use both. Karen Alexander. Jimenez Ibar.
Last name. Doesn't know that.
Oh, okay, I'm sure. First name's Elia.
Yeah.
And David Cassidy. Eric Crawley. Glenn Davis. Andrew Evans. Zachary Volz. Brian Hatton. Francisco. Say it again. Eureka's. To make some notes. Alexander Hauser. Long. Tian Wong, H-U-A-N-G. How do you say your first name? Ken. Okay, Graham Keeler. Stephen Kuntz. Enoch Hay. Abigail Marlu, Yuki Nakagami, Nakagami. I don't know why I like this. Well, I guess it would be. Okay, so in a study, investigation, etc., you have an experiment, and the experiment generates data. So that's like the undefined term in statistics. The experiment generates an observation. And the experiment could be very elaborate, like some chemistry experiment or something. Or it could be like running a car into a stone wall at 10 miles an hour. Okay? And the observation you generate is the amount of damage. And you could usually generate a string of observations. But you might just be concentrating on one or two responses. Okay? And what you really want to do is try to get back to the experiment. What is generating the data? So in statistics, you should always think like this. There's something generating the data. It's actually like a probability model. So back here you have some generator, and then on this side of the wall, there's data. Okay, it's like data comes through the wall. Now data is usually very expensive to get. Good data. Dismiss it together. But you're just drawing the sample data from this model, okay? And in real life, you're never on the left side. In fact, you can't get to the left side. Okay? You really don't know what's generating the data. You just have these observations, and then from the observations, use X's for the observations. Okay, and somehow you summarize these maybe into a statistic or many statistics, and then you try to infer about. What's that dash line over here? Because you make your inference. Now in class, okay, we can generate the data. We know what generates the data, and we can look at our statistics and see how well they do. But in practice, when you have a real experiment, you can't. So you're just making inference. Then you might do another experiment. You might generate more data, okay? But you'd like to make sure conditions stay the same, or you just have another box. Now, I drew a picture like this. This would be like a probability distribution, and then I don't know if you had some bars here. Maybe this is A and B. Say 100 or 200 to 200. And the model is generating most data between 100 and 200. So most of your X's, if you just generate one sample here, would be between 100 and 200. So then you might take this data that you generated here and then just form a histogram. Maybe it looks something like this. And then that histogram is your estimate of this generator. So now, if we could do that, we could, let's just do an example. I'll show you what I mean. Let me get this set up. That's the one reason I want to use R. I'm in R. Okay. Then let's generate some data. Maybe you say we want to generate heights of adult males or something. Or about, we talk about the normal distribution, but again, we know about it, right? Because you've got to do some methods. So we could generate the data. Okay. So I'm going to generate the heights of say, 20 adult males. Or let's generate 15. We call HT for height. And it's just, I'm going to round them. So it looks like real data. See, we're on the left side of the wall. See, this is the left side. I know what generated this data. It's a normal distribution. The mean is 70 and the standard deviation is 4. And I know it's rounded. All continuous data will be rounded. You can't measure it precise. No one's 68.3 inches tall, it's 68.3, blah, 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 blah. And actually it depends on when you measure the person, right? Maybe if this was a real important experiment, you would have a condition set down. The person is measured at precisely 5 o'clock in the morning, the alarm goes off, he stands up and you measure. You measure its height because over the day you shrink, right? Gravity always wins out, so you get shorter. But anyways, in an experiment, things like that may be very important for height. But this would be the right side. Well, I can draw a picture of the generator. First of all, here's a picture on the right side. Looks normal to me, right? There's a histogram of 15 observations. You certainly would infer that in the population, no man is between 66 and 68 inches tall. That's what this says, right? So even in your mind, you're starting to blend that in. But then here's a picture of the generator. Now you know the rest of the review of the normal distribution, right? The mean is 70, the standard deviation is 4. If I go out 3 standard deviations, I have 99% of the data. So that should be adequate for a nice picture. So I should start my sequence at 70 minus 12, which is what, 58? And I should probably go up to 70 plus 12, which is 82. Let's go in steps of what? 0.1 and 0.1. And then I just want to plot. In fact, I should do both of them. So we have a side-by-side plot. I'll just plot the density first. Density. So there's my generator, right? And then, so that's the left side, and I got it on the left side, and here's the right side. You see, that's all the information you have, but this thing is an estimate of this. You just made an estimate. It's not very good. Very poor estimate. But you have 15 data points. Well, in a sense, you only have one unknown in the mean. Well, maybe it's standard deviation too. But in many experiments, that's a lot of data. You're happy if you have 10 observations per parameter in a complicated experiment. You're overjoyed. Often you only have like 5. So often you don't have that much information. Sampling is very expensive, okay? If you do an experiment like on suppose we're in a shop, like an assembly line, and you know a way of speeding it up. So you tell the boss, I need to do an experiment. Okay? We have to shut down the assembly line each day. And the boss looks at you and says, what? Shut down the assembly line? As soon as that shuts down, I start losing money. So he's not going to let you do too many experiments. So data is often very expensive. Okay. Now, what we want to study on what we want to review is some of these probability models. Okay, then we want to review you a few simple inference techniques, and then we can really start on the codes. So we kind of, data comes in two forms, well, actually more, but for this class that'll be fine, two forms. It's either discrete, I use the term discrete, everyone gets upset when I use it. I should just say categorical. All right. To me, it's either discrete or continuous. Sometimes you think about, well, we will talk about the different types of discrete. Okay. But this height would be continuous data. And how about a sample on Obama's rating? Okay. It's probably running about what, 5%. So this here's the sample for Obama's rating. Okay, and you again you can watch the generator. So we just asked 100 people. Let's say 50 people. Do they like the way Obama's running the government? And here's your answer. 1 means yes, and 0 means no. So okay. This would be categorical data. It's just zeros and ones. It's a very simple experiment. But even though this is a very simple experiment, we spend millions and millions of dollars every year on this experiment. Actually, on the experiment with the president. When I was a kid, I mean, they did the rating like once a month, if that. But I think Clinton changed it. They used to do it. I thought they did the rating every hour for Clinton. Okay. Now, it's usually like a Gallup poll, so it's not 50, it's about 1,500. You have to randomly select these people up. We'll drive that home in this class, all right? There's no call-in polls, they're not allowed. I can't do, if you give me data from a call-in poll, I cannot do any inference whatsoever. In fact, I won't do any inference. I wouldn't touch them. Right? So you've got to randomly select these people in some sort of randomized form, okay? And you want a very short time interval. All you need is a crisis in the Middle East to spike this probability that you're trying to ask. Okay. Well, we could see how well we did. See, behind the wall it's 0.55. So behind the wall it would look like this, right? It's yes and everything else, okay? You rate yes. Because you'll get people that say, I don't know. All right, Obama who? All right. I never answer anything whatsoever. So, but that's what's behind the wall, right? And then we could see how well we do. .56 was pretty close. So now I have to go by a lot of tape. Okay, any questions on that? See, that's why I want to use an R test. It's so easy. I can just generate data. I don't have to worry about clicking. Many tab, I have to find a menu. Actually, when I do many tab, as you'll see, I use the old commands anyways. Okay, so let me two types of model. There's more, but that's, again, this will suffice. And that's data too, okay? Data will follow. And one type is discrete. And if you don't want to use that term, please use categorical. And the other type is continuous. And these are your measurements. I mean, most of the time we go with measurements. One of the bad things you see in the lab is when people bring in experiments, they start with continuous data and then they convert it to categorical. And then all you have is the categoricals. They've lost a lot of information. So I always tell them, no, never do that. Stick with continuous as long as you can. Because it's, in a sense, it's more powerful. Okay, well, so let's just talk about discrete for a few minutes in this class. So when I talk about discrete probability models, in the discrete case, the range of the variable, go back to this. The range of the variable is discrete. Which you can interpret as finite, or you can just list them, right? And there's plenty of examples. We just looked at the longest grading. Okay, so here the categories are 0 and 1, right? That's the range of X. And then this is the probability model, right? What else is there? It's the range and the associated probabilities. You want the probability, you might call P, probability X is 1. And Q is probability X is 0. Okay, what else is it? That's the model, all right? P plus Q is equal to 1. If you don't want to write Q, you can write 1 minus P. That would be a long grading. In the book, the first example I have this data on, I had data on the hair color of Scottish children, and I had so many I just turned it into a probability. Oh, okay, and then you always think in terms of pictures, so here's your picture, right? Here's 0, and here's 1. Here you might connect them because these are sort of like numbers. We'll talk about this from time to time. It's not important. But P would be the height in that rectangle, and Q would be the height of this rectangle. And you could do a pie chart if you want. Who's the Scottish? Who's this thing? Oops, that's not this. That was a mistake. I have to in class. There you can see it's a history, right? gets the hot, biggest part.
Right.
Now, this is hair color. They aren't numbers, so you can arrange the categories any way you want to, okay? If you have numbers, it makes sense to arrange them in order. I mean, why? You'll just confuse people, right? You know, suppose you have a number of kids in the family, so that they have the categories of 0, 1, 2, 3, 4, etc. Why would you put number 6 before number 2? If you did that, you know, people would look at you. So in this case, it's just hair color. And it's medium. I don't know what medium is. The categories are medium, fair, dark, red, and black. Okay. Black doesn't occur too often in Scottish school children. This is about 1900 or so. So they're probably very Scottish. I thought I did this machine. I can't seem to read good. There it goes. Okay, so that's a Scottish. Now I'm going to get this. I'm not touching it. I had so much data here, I just took it as a distribution. This would be my probability model for Scottish school children in the 1900s, early 1900s. You see the categories here, this is 26%, here's the median, 22%. And how do you present this to people? The most pleasing plot is to go down or to go up, all right? In fact, it has a name, I don't know if I had it in there or not. It's Lodi or something, if I remember right. But this is the most pleasing plot. Here you don't want to connect the bars, there's nothing, you know, dark is not 3 times better than medium or anything like that. We're just categories. So this is a really big category. And maybe, let's go back to the number of kids. I don't know if I have that in here. I'll have the number of daughters. The next distribution I looked at in the book was the number of daughters in a family of size 4. So you could have no daughters, 1 daughter, 2 daughters, 2 daughters, and 4 daughters. Okay. Now this is this picture is under the assumption that boys and girls are equally likely. And that has come to be, right? It's changed. 51%, females 49%, okay? Because males tend to die at a higher rate in mortality. But now I think it's close to 50-50. Okay? But under that assumption, this would be the number of daughters, so the probability of getting 2 daughters is a peak there. And it's above 0.375 million. So that would be. Now in this case, this is twice as many daughters as this category, 3 times, 4 times. So you would think of this, you might call this like ordinal data with the numbers the way you estimate. And then it sort of makes sense to put the bars together. Then another example, I don't know if I have a Poisson here or not. Well, we'll just leave family undefined because we do many things today, right? But just think of the number of children in the family, and you could have none, right? Or 1, 2, 3, etc. And then there should be some upper lid, right? But then it's like that family that's on TV, they're up to 20 kids. And if you think about it, that's not important. The max is not important. And when you do a model, if the max isn't important or the extremes aren't important, just leave them out. You don't need them, okay? Don't make work for yourself. So this just goes on forever. So that would be the probability model for this, right? You would have P0 would be the probability x is 0. P1 would be the probability x is 1, etc. Okay? And then if you add up all the p's, you should get 1. And this was a course with some math, and we will talk about that. In this class, we don't have to. We just assume that the model we have, that's going to be true. Now, when you get data for this model, only it's a different story. You don't have all these dots, okay? You're going to have a finite number of data points, and you know, you might, the max in your sample might be 6 kids. You might have a family with 6 kids. Okay. So then, how are you going to analyze that data? And it becomes, you know, you might have. Well, we could generate that. That's the last thing. Right? Let's see. It's just generated. I think it's what? How many? What's the average number of kids per family now?
It depends on the definition of family for sure.
So here's my sample. I just asked 50 families how many kids they have. That's my data. Then we might as well just make a picture of those. We'll just see what table it is. That's not a very good example. Darn it. It's not showing me what I want. We have 2 families with 5 kids, those were the max. But you could have like 10 kids, all right? Suppose in your sample you picked out a family that had 10 kids. So that would be part of your sample. And then you'd have this break from 5 to 10. But then what you might want to do is, now you start changing things a bit. You might decide, well, I'll put those frequencies together. So you might have like greater than or equal to 5 or greater than or equal to 6. Okay. So you have to keep that in mind when you do this. You'll get a different answer. See, like the Obama thing was unique. And Scottish hair color, in a sense, was unique, right? But when I start changing these categories, then it's no longer unique. And I can change the categories, and you can change the categories, and our inference will lead to maybe different answers. So you've got to keep that in mind. Okay. Is there any questions on the discrete model? Again, it's just you have a finite number of categories, and you can list them at this number of kids. You don't want to have a max. These occur all the time. A good example is the number of people in the queue. Okay, we'll talk a little bit about the Poisson next time. I love the Poisson distribution. I told my classes, you live in a Poisson world and you should know it. Okay? Most administrators don't realize it. It's always boggles my mind. But the number of people in the queue at the checkout counter, et cetera, there's like a list that goes on. You could say, oh, it's only going to be 5, but then you come and there's 10 people in the queue. A single queue at the bank. The number of people in the queue would be an example of a discrete distribution where you don't have an upper limit. Okay, so what the discrete model is, you have these categories, and for each category you have a probability. And then you can see your inference, right? You're going to take your data, table it, just like we did in this example here. And then what's the estimate from your sample of having a family with 3 kids? Well, there's 50 altogether here. So my estimate is 0.18. Right? 9 out of 50 is 0.18. And how about this 5? Well, even though I have 2 5s, I don't interpret it as 2 5s. I interpret it as 2 equals 5. So if you tell me how many families have, what's the probability a family has 5 or more kids, I'll give you the answer. It would be 24, right? Seems pretty high. Okay. And then just saying that, another piece of that piece would be, why not just check the whole distribution with the split test? Right? So we can talk about that. So we'll begin with that next time, and then we'll I'll stick to the book. So if continuous comes first, I'll talk about it. Okay, so we're off. I'll be in review for about 2 more classes.
Mine always suck. What? Edith's book, she left it here for me. This one is better. I know. Actually, I was hoping it would have Hello Kitty on it or something.
There's 4 floors. How do you get up?
Mighty pink.
Oh, you just take the elevator? Oh, okay.
You can do stairs too.
Regression analysis. It's